Hello, welcome to the second talk about streaming algorithms in the course about the theory of computation. This talk continues the previous talk. In the previous talk, we talked about computational complexity from a wide perspective, and then we gave streaming as an example that we will focus on. The streaming scenario is that a lot of data arrives sequentially, and our goal is to do something useful with it. And in the previous talk, we gave a few options to useful things we can do with it. And today we are going to define it more formally. But before a formal definition, I want to give a few examples that you can keep in mind when we provide abstract definitions. So there are three examples I want to discuss. The first, in the first example, you can think of the stream as the stream is a list of numbers, but you can think about it as the names of people that, let's say, go into a subway or something like that. And the question we want to answer after we saw some amount of people is how many people are there? How many different people are there? So in this specific example, there is 1, 6, 2, so these are 3 people, 5, 4 people, 18, and 3. So these are the names of the different people, and when I went over the stream, I needed to remember at every point in time, is the new element I just saw, is the new thing that arrived in the stream appeared previously or not? This is one thing I needed to know. And the other thing is, what is the total number so far? So there are two things I kept track of. And you can try to see if there is something non-trivial, some non-trivial algorithm here. You can try to imagine to see if you can think of a non-trivial thing you can do here. Okay, so this is one example. This is the number of distinct elements in the string. Okay. The second example is slightly maybe easier to solve. Here, the stream again is a sequence of numbers, and we think of each number as a name of a website or address of a website. And the question we want to answer, for example, is what is the name of the element that appeared the most? What is the name of the website that was visited the most? So in this case, from a quick look, it looks like 7 is the most frequent. So it's maybe a little bit easier to solve, at least in the example when you look at it. And maybe later on you can think about ways to make make this formal. In what sense this problem is easier than the previous? Maybe they are not. This is the second example, the most frequent element. And the third example is maybe slightly more elaborate. So here there is some graph. The graph, the vertices of the graphs are numbers, integers, and the stream of data is addition and deletion of edges, of connections between two vertices. And you can think about these operations as addition or deletion of edges inside a social network. So the graph represents a social network of friendships. And the stream is, there is a new friendship or there is a friendship that should be deleted. So let's say that this is the starting point of the first graph we start with. And then the edge 1, 2 is added. So this is the first item is add the edge 1, 2. So this is the new graph after we add the edge 1, 2. Then there is the edge 1, 12 that should be added as well. So we add the new edge 1, 12. Then the edge 2, 4 should be deleted. So this is the edge 2, 4 being deleted. And then the edge 3, 6 should be added, but it's already here, so the graph does not change. So the social network is updated through time. And the question we want to answer is, inside this huge social network, what are the 10 vertices with highest degree? What are the 10 most connected users or members of the networks? So this is a slightly more elaborate story, but it's a very natural story. And you can ask many questions about a social network. This is just one example. Okay, so these are the examples, the 3 examples. And now you have them in your mind, so you can think about these examples when we talk about the formal definitions. So now we are going to define the model. Our goal in this computational model is to compute a function, f, and this function takes as input, this is a finite sequence of elements in X. So there is a set X, and X star is finite sequences of elements from X. And the function takes as input some finite sequence of elements and gives the output is in some domain Z. For example, the first example we saw is the function that assigns a sequence of elements, the number of distinct elements in this sequence. So this is one example of such a function. So a function of this sort, of this type, is the thing we want to compute. Our model will focus on one specific computational resource, the memory size, the size of the hard drive, or some other way to store information. And the way we will model it mathematically is we will have the memory, which is denoted by capital M, will be a string of bits of length m. So we will have m, little m, bits of memory. So this is the computational resource we want to focus on. So the goal is to compute a function of this sort, and the resource we want to model, to focus on, is the memory size. Now we need to define the device. What are the devices we are going to work with? So I remind you that the goal is to compute this function f. Now the device we will call a streaming algorithm. What is a streaming algorithm? There are three components. There is the memory, which is some string of n bits. And then there are two functions, two procedures. One is an update rule. The update rule takes the memory at some time t, and the new data that arrives at time t, and produces the state of the memory after the data arrives. So this is an update rule for the memory. Okay, so this is one procedure in a streaming algorithm, is how to update the memory, the content of the memory. You can see the similarity here with the finite automaton of size 2 to the n. So the finite automaton also has such a definition where you move from some state and some input to a new state. So you already saw a similar definition. But a streaming algorithm also has a dictionary, a way to interpret the content of the memory and translate the content into a decision. So I call it a dictionary. It maps the state of a memory to an output. Yeah, the function we want to compute should output elements in Z. And the dictionary tells us if the state of the memory is M, then the output is D of M. Okay, so this is a streaming algorithm. This is the mathematical model for a streaming algorithm. There are three components. There is the state of the memory M and two functionalities, the update rule and the dictionary. And this integer M is called the memory size of A. So this is how we are going to call it. Okay, so this is a mathematical model. You can see that everything here is defined in terms of sets and functions, which is the way the most basic notions in mathematics. So this is the device we are focusing on. Now we are going to explain the functionality of devices. How does a device compute a function? Okay, so this is the next step we are doing now. So now the input to a device is a stream. A stream is a sequence of elements in X. So it's X1, X2, and so forth. And what does the device do? So let's write it down. So we have the stream X1, X2, X3, X4, and so forth. And at every point in time, there is the state of the memory. The state in the beginning is denoted by M0, which is assumed to be the all zero string. This is a string of length n. Then we take M0 and X1 and use U. So these two things generate M1 via the update rule U. So M0 and X1 generate the new state of the memory, M1. Then M1 and X2 generate M2, again using the update rule U, and so forth. So the device is actually this sequence of states of memory. This is what the device, the state of the device as time evolves. And what do we want the algorithm, what is the property of the algorithm we want to have in order to compute the target function f? We want the property that if we interpret the memory at time 2, we apply the dictionary on M of t, then the output of this interpretation is the value of the function we want to compute on the stream up to time t. So we can interpret M2 as the value of the function on the first two x's. We can interpret M10, and it will be equal to the value of the function on the first 10 elements. Okay, so this is the meaning of the streaming algorithm A computes a function f. So there are many quantifiers here, if you think about it formally, but the quantifiers just represent something natural. So there is a memory that is updated through time, and the algorithm succeeds in computing f if the memory tells us the answer. If the only thing we need to do in order to determine the value of f is to know the state of the memory. So this is the definition of a device computing a function. And now, as in the abstract computational complexity scenario, we can define the streaming complexity of a function. The streaming complexity of a function is the minimum memory size of a streaming algorithm that computes this function. So it is written here in words, and it is written here in a sort of a more formal language or notation. Okay, so now we have devices, or maybe before devices, we have functions, the thing we want to compute. Then we have a model, computational model, which is devices. And then we have complexity theory, which is for every function, we associate its computational complexity. Now I want to move to a specific example that we will focus on to make this a bit more concrete. Before the example, I want to make 3 comments about the definition. So the first comment is that a stream is an infinite sequence in this specific model, and the computation is defined on the entire stream, on the infinite sequence, but we check its correctness only at finite times. So this is one comment. There is an infinite object in the definition, and the definition of compute is actually only at finite times. We never check anything about infinity. So this is one comment. The second comment is that the model we just defined focuses on just one computational resource, which is the size of the memory. And the model captures this in two ways. First, the memory size is this parameter, this integer in the definition. And the two other functionalities in the device, the update rule and the dictionary, are just functions, abstract functions, and we don't care about their complexity or any other property. They're just abstract functions. So the only thing we care about in this model is this number, this parameter n. So this is the way we chose to implement the focus on memory size, is by setting up all of these formal notions. So this is one way to formalize a model that is interested in memory size. And the third comment I want to mention, I will not speak about it in depth, is that in the model I just defined, there is no randomness. I did not use randomness for two reasons. One is that probability theory sometimes can be also abstract, and I don't want to add more abstraction at this point. And the second is that it also adds more quantifiers into the definition, and I wanted to keep the definitions as simple as possible. So these are the reasons I did not add randomness. But adding randomness to an algorithm is a powerful tool, powerful resource. And specifically for a streaming algorithm, it enables to do useful things efficiently. So just keep in mind that if you add randomness to your algorithm, maybe you can do better things. So these are the three comments. And now I want to move to the connection between streaming and finite automata. So again, I will be, this is a connection, streaming is a connection between finite automaton and Turing machines. So right now we are looking backwards. How does streaming relate to finite automata? So the goal of a streaming algorithm is to compute a function from finite sequences to some domain Z. And if this domain Z is the number 0 and 1, it is a Boolean function, then this function corresponds to a language. For example, the language of all the strings that are mapped to 1 via F. So a Boolean function and a language are the same things. And the claim or an observation, which I will leave you as an exercise to verify, is that if the streaming complexity of some function, some Boolean function f is m, so there is a streaming algorithm with memory size m, then the language that corresponds to m can be computed by a finite automaton of size 2 to the n. So the size of a finite automaton is exponential in the memory size of the streaming algorithm. And this is actually an equivalence between the two notions. So far, the streaming perspective and the finite automaton perspective is very similar, except that here we allow to compute non-Boolean functions. We did not just focus on languages, we allowed more abstract computations, more general computations. So this is the connection backwards to finite automata. And the goal of the theory of computational complexity is to understand the complexity of functions of interest. This is the general goal of computational complexity. So let's try to do this for a specific example. So through the example, I hope the example will help to understand the basic definition and to understand how can we compute this number or prove bounds on this number. The example we will focus on is a very simple example. It's a function that outputs 1 if the input is a palindrome and outputs 0 if the input is not a palindrome. So a palindrome is a string that when you reverse its order, it remains the same. So for example, the string 0, 1, 1, 0, 1, 1, 0, this is a palindrome. Or maybe I'll write it like this. The palindrome function on this string is 1, and the palindrome function on 0, 1, 1, 0, 1, 1, 1, this is 0. So this is the function we will focus on in this specific talk. And we will use this function as a way to understand computational complexity more generally. Okay, so before we go into the formal details, try to imagine what is the streaming algorithm you would use in order to compute this function. So imagine we have a sequence, an infinite sequence of bits. Yes, some arbitrary sequence of bits. And now you need to construct a streaming algorithm that reads the sequence, and at every point in time, the memory content allows to decide if the string we read so far is a palindrome. So here it's not a palindrome, not a palindrome, not a palindrome. It is a palindrome, not a palindrome, and so forth. So what do we need to keep in mind? What does the algorithm need to keep in its memory in order to decide this function, to compute this function? And the way we can make your thoughts into a theorem. So the theorem I want you to think about for a few seconds is, what is the streaming complexity of this function? This streaming complexity is the minimum integer, the minimum m that memory size m suffices to decide palindromes in a streaming way, in a streaming model. So the answer to this question is that the memory size required is infinite. There is no streaming algorithm that can solve palindromes in the way we formally set up the model. And this is related or equivalent to the fact that palindromes as a language is not regular. There is no finite automaton that decides it, that computes it correctly. So this is equivalent. Okay, so somehow this is an unsatisfying answer. When a simple problem like palindromes immediately goes out of the computational model, somehow the model is not maybe interesting enough, or now it's a time to reconsider the definitions we chose. And this is what we're going to do next. So we are going to go back to the definitions. The reason we are doing this is that we got this very strong statement, but maybe it is too strong. It is not interesting enough. It is not accurate enough. It is not informative enough. So the way we are going to fix the definition is, instead of being interested in what happens for all times up to infinity, we are going to be interested in some finite time. We add some time capital T to the definition, and the streaming complexity up to time T is the minimum memory size we need to compute this function, but just up to time T. We don't care what happens after time T. So now we added the notion of time to the definition and to the notation. And now, in terms of the course, we added to the theory of finite automata the element of time. This element of time was not present in the definitions of finite automata. And from an algorithmic perspective, we can think about it as algorithms that can increase the memory size as time goes on. So this is a different perspective on this slight change in definition. So now we want algorithms that can, from time to time, add some bits to the memory. And now the main thing I want to prove today, it's a very simple proof, is that now for the function palindromes, we have the streaming complexity as a function of T. This function of T is up to constant linear in T. So the memory size that is required to answer palindrome up to time T is somewhere between T over 2 and T. This is the thing we are going to prove next. Okay? So the first thing we will do is to prove an upper bound. We will find an algorithm. This is a very simple algorithm. What is the algorithm with memory size T that can solve palindromes up to time T? So the algorithm is very simple. The algorithm memorizes the input. So I will not write this formally. You can, it may be a good exercise to define the update rule and the decision, the dictionary that underlies this very simple algorithm. It just memorizes all the input, all the data it sees, and then makes a decision. It's a very, the algorithm is maybe doesn't do anything interesting with the data. So this is the upper bound. In this case, the algorithm is very simple. Now we're going to move to the lower bound. The lower bound is slightly more interesting, or it is more interesting. And the claim here is that if we want to compute palindromes up to time 2t, the memory size must be at least t. So up to time 2t, we need memory size at least t. And there are a few ways to view this. I'm going to use one perspective that I'm going to elaborate more on in the next lecture, the next talk. So here is how we are going to prove this. So think about the input at time 2t as consisting of x1, x2 up to xt. And then it will be more convenient to add new symbols, y1, y2 up to yt. This is a string of length 2t. Okay, this is the input to a streaming algorithm up to time 2t. Now the first observation that allows to prove a lower bound. So first, maybe I'll use a different color. The memory state just at time t. We just care about the state of the memory at time t. There is some update rule, and we assume that this update rule allows to compute palindromes. So the memory state at time t just depends on x. X is the first half of the input. This is the first observation. This is because, in general, the state of the memory at any time depends only on the input up to that time. You can prove this by induction, for example. The second property that is important for, so this is true for any streaming algorithm. Now, how does palindromes come into the picture? So the second property is that for every x, for every such x of length t, there is a unique y, again, of length t, such that palindromes on x and y is 1. For every prefix, for every left half, there is a unique right half that makes palindrome output 1. What is this y? Y is the reversal of x. This is the only string that will make palindromes output 1. Any other y will make palindrome output 0. Now, the conclusion from these two statements, so the third property we know, this is by definition, is that d of the memory at time t and y, so maybe it's not d, if we know the memory at time t and y, then we should be able to deduce palindrome of x and y. So this is, if the algorithm correctly computes palindromes, then the memory at time t and y should allow us to compute the value of the function, palindrome. And the conclusion from all of these three properties is that the map x goes to m of t, this map that is defined here, is injective, is one-to-one. If this map is not one-to-one, then two x's are mapped to the same state of the memory. But for each of them, there is a different y that palindromes accept. So it cannot be, if the 1, 2, and 3 hold, that this map is not one-to-one. So I'm leaving, so you can write some more formal details if you want, but the intuition, I think, is clear. If two x's are mapped to the same state of the memory, then this state for one of the two y's will output the wrong answer. So this is the conclusion from these observations, and this means that m must be at least t, because there are 2 to the m x's, 2 to the t x's, and 2 to the m t's. So this is the conclusion from all of this. So this is the lower bound about the streaming complexity of palindromes at time 2t. Okay, so the summary of all of this is that the streaming complexity of palindrome grows linearly in time. A corollary from this is that if we want an algorithm to work indefinitely for all times, then its memory size must be infinite. It cannot be finite. And the conclusion in terms of finite automata is that palindromes is not regular. And you can compare this line of thought we just discussed to the pumping lemma, for example, which is another way to prove that a language is not regular. Okay, so this is the discussion of palindromes, and I want to, before we conclude, add one more idea, a very central idea in computational complexity. And the idea is, now we prove that palindromes is hard. We prove the lower bounds for palindromes. This immediately implies that many other problems that are easier than palindromes, that are harder than palindromes, are also hard. So this comes, the general name for this is reductions. We can reduce palindromes to some other problem. This reduction will show that the other problem is harder, because if we can solve, so let's do it, I'll write it. So we can reduce, we can take palindromes and we sort of can embed palindromes inside a different problem. We will see some example of the number of distinct elements. And this reduction will tell us that if palindromes, if this is hard, then this is hard. Or stated differently, if this is easy, then this is easy. Okay? So there is a lot of, or many types of reductions. You will see more complicated reductions later in the course. And you will see the importance of reductions when we will discuss computational classes. But I want to demonstrate it now for palindromes in a very simple example. So the example is that the streaming complexity at time t of palindromes cannot be larger, is at most the streaming complexity at time 2t for the number of distinct elements. So the number of distinct elements in the string is the number of distinct elements we saw, which is the size of this set. This is one way to define it. So palindromes is easier than the number of distinct elements according to this claim. And here is a sketch of the argument. So the way we will do it is we will take an input to palindromes and map it into an input to distinct. And this mapping will show that if we can solve distinct, we can solve also palindromes. So here is how we do this in this specific case. We take an input to palindromes of length t, and we map it to input to distinct of length 2t. So every element in W is a pair of an integer and a bit. So it is 1 x1, 2 x2, up to t xt. This is the first half of W. And the second half of W is tx1 up to 2xt minus 1 up to 1xt. So here the time is increasing, here the time is decreasing, and x appears in the same order. Here it is x1, x2 up to xt, x1, x2 up to xt. So this is the construction from x to W. And the observation behind this construction is that x is a palindrome if and only if the number of distinct elements in this string is t. So if x is a palindrome, then 1x1 is equal to 1xt. So this one and this one are the same, and this is true for all of them. So if x is a palindrome, the number of distinct things we see here is exactly t. If x is not a palindrome, then, for example, x1 is not xt. So the number will be larger than t. The number of distinct elements in W will be strictly larger than t. So this is a way to take an input for palindrome and make it into an input for distinct. And the conclusion from this embedding is functional. So if we can answer this question, we can answer this question. So we built a reduction from palindromes to distinct, and this shows that the streaming complexity of distinct is also linear in time. This is a conclusion from the lower bound we saw before. Okay, so let me summarize this lecture. So this lecture is about the streaming model, which is a hybrid model between finite automata and Turing machine. Streaming adds the element of time into the world of finite automata. And today we defined a model formally using sets and functions in mathematics. Then we focused on one specific example to try to understand the definitions. And we saw that the first take on the definitions was not informative enough. The answer was could be more meaningful. So we changed the model slightly. We added some more data to the definitions. And then we proved, the interesting part was to prove a lower bound in this framework. And the summary of this lower bound is that there is no free transfer of data. If you want to move some information from one place to some other place, you need to pay for it. This is maybe a summary of this intuition, the intuition behind the proof. And the second idea we saw is that we can reduce problems, computational problems. We can build reductions between problems. And this is useful because if we prove a lower bound for one problem, we can immediately deduce a lower bound for the other problem. So this is the two main ideas, main proofs we saw today. The next talk will talk about streaming, but from a wider perspective. And it will be, again, slightly less formal than this talk, where we gave formal definitions and we saw how to use the definitions in order to prove something. So I hope to see you in the next